Hello, welcome back. The learning objectives of this lesson are to set up a heat balance using a building as an example, to use heat transfer equation to quantify rates of heat transfer, to know examples of real energy systems with their characteristics so that the range of systems and where they are applicable becomes apparent to you. Here we go. Let's start with the heat balance of a house. It's cold outside, and there's a temperature difference between the desired indoor temperature and the outside, which causes heat losses. These heat losses consist of the conduction through the roof, walls and windows. It is dependent on the temperature difference between indoor and outdoor and the thermal properties of the materials used in the building envelope. There's also heat loss caused by ventilation. Cold air enters the house, and when there's no heat recovery, warm air leaves the house. Additionally, there is heat loss caused by infiltration, that is unwanted leakage of air through the building envelope. On the positive side of the heat balance, there's also heat gains. The first is the sun. Heat is gained mainly through the window, depending on the amount of solar radiation, the orientation and the size of the windows. There are also internal heat loads, for example electrical equipment in the house such as lamps, computers, etc. And of course, as you remember from the first lesson in this module, the people in the house. When all the heat gains are not enough to compensate for the heat loss, you need a heating system to keep the temperature in the building at the required comfort level. In this example, we simplify an underfloor heating to a 2D surface which exchanges heat with its surroundings, a room in a house to meet a given demand. To design the heat supply system, the heat transfer equation is introduced to you on the slide. The heating power that this surface area transfers depends on the material of the floor, which is fixed once you have installed your underfloor heating and the floor on top, the surface area of the floor, which is also fixed, and the temperature difference between our floor surface area and the desired room temperature. The desired room temperature is also fixed, so to control the heating power you have to control the floor surface area temperature, which depend on the supply temperature and the flow rate of the water through the underfloor heating system. With fossil fuels, it's easy to get high supply temperatures as we burn gas at over 1000 degrees. Therefore, radiators in such systems are much smaller surface area than underfloor heating. Following from what we learned in this lesson so far, we have two main things we need to change in existing buildings or processes to do differently in new buildings and processes to facilitate the use of lower supply temperatures for heating. The first is to reduce peak heating demand, like also discussed in previous lessons. This seems like an open door, but many people, including professionals in the field, often forget. This is commonly done by insulating, which has a major added benefit that it will also reduce the total required heating demand. Second is to increase exchange surface area, for example within the walls and floors of the buildings. This will help us to find sources of heat that fit the temperature level of the process we need to heat or cool. An additional benefit of using building mass is to create flexibility. The building mass won't change in temperature quickly. Also, this type of heat transfer is more comfortable as heat is released evenly distributed around the room rather than at a specific location at a very high temperature, being dependent on free convection by air to heat up the entire room. Please bear in mind that despite efforts to reduce demand, you may still need conversion and storage to be able to utilize a local renewable source of heat. For conversion, commonly heat pumps are used to provide heating to an underfloor heating as depicted on the slide. In a couple of weeks, in the energy components module on heat, we will go into more detail on the heat pump and storage. Let's move on to the example projects that I've promised you. The first project I would like to discuss is in an individual house in Delft, or rather a set of individual houses, each built with their own renewable heating and cooling systems. The houses were built in the year 2020 and designed to be energy neutral across a year, which means they may have a surplus or deficit of energy at any moment, but over a year they balance out. Each house is highly insulated and fitted with a closed-loop Boral heat exchanger of 150 meters deep to get heat from the underground. A heat pump is used to provide the temperatures needed for both heating and cooling, which is transferred to the house via an underfloor heating system. The electricity use of the heat pump is supplied by solar panels installed on each house. In this neighborhood there are around 150 of such systems spaced closely together. Because they take heat from the underground, planning was needed for the design to ensure that the systems do not interfere. Balanced heating and cooling loads help with this. The second project is a moderately large education building on our TU Delft campus called ECHO. The building is designed to be energy positive, which means that not only cover 100% of its own energy need, but also provide energy externally. The building is highly insulated, reducing the required heating and cooling and the required supply temperature. It has passive energy features such as solar shading of the window, which still provides substantial amount of light. Also, the heating and cooling load is designed to be balanced such that a seasonal energy storage using aquifers below the building ensures that the thermal energy available is utilized. Lastly, the heat pump in the system is supplied with electricity from the solar panels. The next project is one of the world's largest solar thermal parks located in Silkeborg in Denmark. It produces a maximum power of 110 megawatts. It is connected to 20,000 houses and supplies a maximum of 20% of the total heat demand. The solar thermal energy is highly variable and that is compensated partly by having storage tanks, but mostly by using flexible fuel-derived energy. The CO2 savings is approximately 15,000 tons per year, and the system was built with a limited capital subsidy from the government. The final system is the first urban geothermal project in the Netherlands. There were several deep geothermal projects for greenhouses before this in the Netherlands, but none in the built environment. Both houses and commercial buildings are supplied with around 1,000 individual connections. A total of around 45 terajoules are supplied annually, which makes up around 75% of the total heating supply of the heat network. The peak demand remains to be covered by gas-derived energy. Now, let's summarize our learnings. We discussed heat losses and gains in an energy balance and how to quantify heat transfer to supply heating. We also discussed how fossil fuels create lock-in for high supply temperatures, and we need to insulate and increase heat exchange surface to accommodate for lower supply temperature to enable renewable heating. And last but not least, I showed you various examples of heat supply systems introducing various technologies which will be discussed in the heat components module. Thank you for your attention.